Hey everybody, I'm Mr. Baker. This is the first video of our first unit for biology and honors biology. What you're seeing now is the slides. Those are available on Canvas if you want to see those directly. I advise you make a copy of those and put them into your own Google Drive. Organize that in a way that you can find them well. All right. I'm going to click through them and lecture just like I would lecture if we were in class. Remember that these are our notes. You should be taking notes. The next day, when they're due, I'm going to go around the classroom and check everyone's notes. If you do not have them, they will go into the gradebook as missing. Make sure you're at least writing down what is on the screen. I advise you to also hit pause, make sure you've got everything down, and take your own notes on what I'm saying as well, because I'm going to do more than just read you the notes. I'm going to talk about it, just like if we were in class. All right? Sometimes my face is going to be up on the screen like this, and if it looks like I'm looking off to the side, that's my second monitor where I've got control of everything. So sometimes we got to do what we got to do, right? So let's go ahead and get started, right? So we'll make my face a little smaller and we'll get going. So first, we're going to talk about why we study science, all right? So way back at the beginning, right? Genesis 1, we see God creating everything in 6 days. We're going to talk about the story of creation later in the year, all right? But remember, 6 days, seventh day he rests, right? But right after that, he tells us in Genesis 1:28 something called the creation mandate. Right? The creation mandate is God saying, you, mankind, are control of everything in creation. You need to take care of it. Right? God uses the word steward there, or at least in whatever language God spoke to Adam and Eve in, translated to English. It's the better word is steward there. Right? So, the reason we study science is because it allows us to be better stewards of creation. It allows us to take care of creation better. Right? So, in science, we study things and we try to determine what is true. Right? We try to determine facts. Some ways we might think about truth is it accepted? Is it something that works? Is it something we can see, observe? We can take notes on, right? Can you smell it? Can you taste it? Can you feel it? Is there some kind of magnetic field that can be observed through the use of magnets and sensors? Does it have a temperature, heat, right? Is it something that happens all the time? Is it every day, like the sun rising in the east and setting in the west? Or is it something that we only see very, very infrequently, like Halley's Comet or other cosmological events? Or is it something that only happens once and it can't be observed any more than that one time? And we might think about truth as something that is logical. Does it make sense when we think about it? When we put it to the test, does it actually make sense? All right. For us, though, we're going to talk about absolute truth as the thing defined by God. And all other truths are based on our own observational skills and understanding of creation, which are incomplete. Right? So that's the reason that science can change, right? We make new discoveries, so science changes its understanding of that thing, right? Before calculus, we had a hard time describing some of the larger space level movements of things and some of the smaller, very, very small movements of things. But after we discovered some of the laws of calculus and upper level maths, we started to have a better understanding of that. Now we're more on the quantum level, where we're looking at the position of electrons inside of atoms. Right? But God's truth has always been absolute. It is not changing. Man's truth, man's understanding of creation, changes as we are better at making observations. Right? So this is a definition that I want you to know. Right? This is our definition of science as a whole. All right? It's got two parts. The first is kind of the facts, and the second is the methodology, how we do science. Right? So the collection of observations, inferences, and models, right? That's the facts, right? That's what you're going to find in the textbook. That's what we're going to spend a lot of our time about. All right? And through a systematic study of nature, so that systematic study of nature, that's the methods, that's how we do science, the verb part, right? And it enables humans to exercise proper dominion over God's world. So science as we are going to study it and describe it, gives us the ability to be better stewards of creation. I'm embedding our idea of God's task for mankind to the creation mandate inside our understanding of science. And if we're going to apply this to biology, right? Bio means living, right? So we're just going to apply all that to living things. And that's what we're going to do in this class. We're going to study how living things, all right, work and operate and work together. Right? We're going to go all the way from cell level to biome level throughout the year. Right? And we might talk about these observations, inferences, and models more specifically all throughout the year. All right, the scientific method, I'm going to actually remove my webcam here so you can see the whole thing. These are the steps that I like to think about, but remember that it's not really a set of steps. You can jump in anywhere along this chain of events, and based on things that happen, you might even go back a step or two. All right, you might be testing your hypothesis, and your conclusion is that it doesn't work. So instead of immediately sharing your results in the report stage, you go back and research more. You make a new hypothesis. Right? One set of conclusions can lead you to a completely different set of conclusions as you move through this kind of experimental chain of events. Right, so when we write hypotheses, I kind of have a shortcut for it, and that it is always a statement, not a question, and if you use the if-then layout, things get easy. All right, it is always something you can test as well. All right, so I've got two options here, one with a green check, one with a black X mark, right? So if I never water my plant, then it will dry out and will die. So the thing that we could do to test is change the ability to water the plant. Is it getting watered or is it not getting watered? And then we've got something to see if it's happened. Dry out and will die. So we can tell if that plant is wilting, it's drying out, or if it's dead or not. All right, so it's testable. The second option, if I sing to my plant, then it will be happy. Right? This is actually based on an old wives' tale, that happy plants grow better. All right. So if I sing to my plant, that's a thing we could do, right? We can play music for plants. We can have someone come in and sing to them on a regular basis, right? Then it will be happy. We can't test if plants are happy or not. So this is not a good hypothesis, all right? The first part's good, but that second part is where the problem lies. All right, when we're looking out for hypotheses, all right, and you're going to write a few of those this year, make sure that they follow these kind of rules. And if these are in your notes, you can come back and look at them later, right? So your hypothesis should not be an opinion. So don't start with I think that or I feel like, right? We're just going right into it. And if you're using that if-then statement, it's going to be easy to make sure that you're making a claim and that it's testable, right? If the only way to test your hypothesis would be to cause like mass destruction or involve a black hole, something that could only do once, not a good hypothesis. When we use words like could or seems, we're being very vague. We're not being precise with our words, right? We're not actually nailing down exactly what we mean, what we think will happen. So we're going to try to avoid those. Then is the idea between independent and dependent variables. Independent variables are what you are going to change in the experiment. All right, so in that last example of the plant being watered, we could change if it's watered or if it's not watered. And dependent variable is going to be what we're measuring. All right, so dependent is measured. And so we would measure if it lives or dies, if it dries out or does not dry out. We could use like a humidity sensor or a hydro sensor to see if the soil stays wet or if the plant loses its ability to stay wet. All right. So when we're doing our experiments, we're always testing the hypothesis. Is it a correct hypothesis or is it an incorrect hypothesis? We might use terms like, is the hypothesis supported or not supported? Right? As long as we're only changing one variable at a time, we can be sure that the thing we're changing is the cause for the change in the dependent variable. right? And then anytime we do experiments, we want to have a control group where the experimental treatment just isn't happening, right? So with our plant being watered or not watered, usually plants are watered. So that's going to be our control experiment. Our non-controlled group, our experimental group, is going to have that lack of water. All right. We already talked about independent and dependent variables. If you didn't write that down in your notes, now's your chance. Right? A constant, just like in math, is something that's not being changed. Right? And then, like we said with that last slide, a control group, nothing different done to it. It's the same as it normally would happen in nature. Right, so here is another example that I want to talk through. For this one, a plant is being watered with different liquids, right? So you can see on the right side, we have a control variable of just giving it plain water, everything that would happen in nature, all right? The experimental groups are A and B. For those, we've changed that liquid to cola or juice, right? And then you can see across the top, it walks you through what an independent variable is, a dependent variable, and a controlled variable, or a constant. That's just a different word, same meaning. Right, so the independent variable, we're changing the type of liquid. The dependent, you can see that there's a ruler on each plant, so we're measuring its height. And then the controls, or the constants, you can see that we have the same kind of plant across the field. Each of them are in the same pot size. They're probably even the same type of pot, like same plastics or same terracotta. Each one is getting a measured amount of liquid. I know that that's not really in the picture, but that would be one of our constants, right? We would have planted those plants in the same type of soil at the same time. We would keep them in the same location so that they have the same temperature, the same humidity, the same airflow, right? You can very much dial in your constants to make sure that you're only testing one independent variable. All right, now, when we're taking those measurements, we're going to describe them as either quantitative measurements or qualitative measurements, all right? Quantitative, you can hear that word quantity in there, so we're always going to be dealing with a type of number. Qualitative, you can hear the word quality in there, so it is a descriptor. All right, I've got some examples here on screen. Make sure you've got at least a few of those down. We're going to go over some stuff in class on recognizing and describing data as quantitative or qualitative. All right, then I want to talk to you about probability. All right, because in science we also have to do a little bit of math, and one of the things that we do with our math is probability. It's how likely something is to happen. So on these six-sided die, right, the most likely result is a 7, because you can get that with 3 and a 4, a 6 and a 1, a 2 and a 5, and then reverse all those, right? A 5 and a 2, a 1 and a 6, a 4 and a 3, right? All get a 7. So that's the most likely, right? Each of these has a probability of 1 out of 6 for each die, all right? Face to be shown up, right? But if we're going to talk about something bad that's happening, all right, if we're talking about something bad that's happening, that word probability is going to change to risk. Risk is still probability, all right? It's just something I want to talk about. You don't have to have that down in your notes, but I want you to recognize that if we're talking about the risk of something happening, that's still probability. And when we talk about modeling things in science, we're going to talk about one of 4 types of models usually: physical models, graphical models, conceptual models, and mathematical models. Physical models are like this one on screen here. It is an actual thing you can touch, you can feel, you can see. The skeleton in my room is a physical model of a skeleton. It's not a real skeleton, it's plastic, right? The graphical models you have seen. If you open your phone and look at the weather app and there's a radar on there, that's a graphical model, right? Any 3D rendering of a shape or a space, that's a graphical model. The map on the wall for the fire exit and tornado drills, those are graphical models of information, right? Conceptual models are going to be a little bit looser usually. They're going to talk more about relationships or the probability of something happening or proportions, right? So things like diagrams and drawings where there's not hard and fast numbers on them. So like an architectural drawing is going to be more of a map than what we're talking about here. But if you sketch something out, that's going to be a drawing. And then verbal descriptions always fall within conceptual models, again, unless we're starting to add numbers in the mix. When we do have numbers in the mix, they usually become mathematical models, right? So in math, you've learned like the slope equation, y equals mx plus b. That is a model of the actual line that you would draw in a graphical model, right? So we're still representing the same thing, just different ways. The beginning of our lecture talked about how science is limited, right? Scientific method is kind of brought down in a few different ways. So because it's based on observations, we can't do anything that isn't observable, right? Our biases, our beliefs, our errors in measurement can change things. NASA crashed a Mars lander into the surface of Mars because of a measurement error between metric and US standard, right? It is a problem that happens in the scientific method, in engineering. When we can't control an experiment, like, say, weather being out of our control, right, that is a problem, right? So if you're studying birds and it's rainy, you're not going to catch as many birds to get as many samples because the birds don't fly as much when it's raining. Right? The other is universal statements, like, I always blow dry my hair in the morning, or I never have a bad hair day. Those are always things, right? Universal, right? I always do this, I never do this. And we can't test that because we would have to check every single day if those were true or not. Or every single option to see if it works or not. And then workability is a term for like the feasibility of something. Can we afford it? Does it make sense? Would it be too convoluted and complicated to test? Right? Those are all problems, right? If you want to write down all 9 limits of science in your notes, I highly advise you to do so. This is something that Mr. Baker would ask you on like an exam, right? On a test or a quiz, right? I talked about a lot of those today, but this is kind of me putting them all together for you to write down in a list. So hit pause, write all those down. All right, we're going to talk about ethics in class a little bit through the Tuskegee experiments, right? But ethics are our guidelines of what should and should not be done. Christians are going to answer to God first and foremost, look at Scripture, look at what the Holy Spirit leads us to do. But as scientists, we also are going to answer to things like the United Nations. They have a branch called COMEST, the World Commission on the Ethics of Scientific Knowledge and Technology. If mad scientists were a real thing, this is where they would get put on trial, all right? Aside from breaking laws as well, right? These are going to say, no, you shouldn't test on children. No, you can't do blank test. Yes, you can do blank test, right? Usually if a scientist is working for a university or a college and doing research there, they also have to get approval. All right? So that's where we're going to end today's session. Sorry about switching those screens around. I clicked one too far. Remember that these are our notes, all right? You need to have all these notes down. You need to have 2 questions, all right? Bring 2 questions about anything that was in the notes, all right? Something you didn't understand, something you want to learn more about, something that you were kind of confused on, all right? Anything like that. If it's something that I can walk through the notes and read, that is not a good question, right? Bring it a little bit past that, right? I just want to push us a little bit to ask 2 questions, all right? This time, I'm going to be a little bit more lenient on how good those questions are. But throughout the year, as we go through our 30-some lectures, you're going to have to be asking better questions. Sometimes it's going to be 2, sometimes it's going to be 1, Sometimes I might even ask you to answer a question, right? For now, make sure you have all these notes done. Make sure you bring me 2 questions tomorrow, and I will see you then.